Hello again, and welcome to part 2 of the Demystifying Fiber Optics series by the FiberWizards. Since we have already made it very clear that fiber optics transmit light signals, let's talk a little bit about how light behaves. The first thing is that light travels at the speed of light, which is equivalent to about 300,000 kilometers per second. In other words, very fast. The space through which the light signal travels is called a medium. Examples of these mediums could be simply the air or fiber optics themselves. When light passes through a physical medium, the material limits the speed, so when light travels through fibers, it actually travels a little slower than traveling through air. This makes it so that when light crosses from one medium to another, such as from air to water, at open angles or with little perpendicularity to the surface, it penetrates and the incident ray bends and changes direction. This phenomenon is called refraction. As we can see here, the incident beam, the one coming from the laser, changes its trajectory a little as it transitions into the new medium. This is due to the differences in refractive indices which causes the light to bend. Another phenomenon observed in the behavior of light is called reflection, which in simple words refers to the fact that when an incident ray collides with reflected surfaces, it bounces. In fibers, although light remains trapped in the core as it travels through it, at the point where the light enters the fiber and passes from air to glass, there is a certain level of reflection, which if too high could create issues or damage the system. As we said at the beginning, the difference in refractive indices between the core and the cladding of the fiber means that when an incident ray hits the surface between the zones at very open angles, the light is reflected back into the core. This phenomenon is known as total internal reflection. To demonstrate this effect, we will use a fish tank filled with water and a laser pointer. Then, we'll point the laser from the bottom up until the light hits the edge of the water. With this example, we can see the effect of internal reflection, which occurs when the incident ray hits the water and air boundary, bounces off, and returns to the water. In order for an incident ray to enter and travel through the fibers, it would have to enter at an angle within a specific range known as the numerical aperture, or given its theoretical shape, also known as the acceptance cone. If the beam enters at a sharp angle, as shown here with the red line, the light will refract and escape as it passes through the cladding. As long as the incident beam enters within the accepted numerical aperture range, it will remain trapped as it travels along the fiber. Here, with an acrylic rod and a laser, we're going to simulate the effect of total internal reflection. In this case, when the light hits the acrylic to air boundary, it bounces off and returns to the core, remaining trapped along the path of the light guide. This explains how telecommunication light signals can travel long distances through optical fibers. Well, this is the end of the section. Please take a few moments to complete the corresponding quiz, and when ready, please continue with the next section.